right? Not a surprise. So load instruction 1 here feeds into instruction 5. Load instruction 2 feeds into instruction 7. This graph clearly shows sometimes load instruction 2 will complete before instruction 1. So should we have actually reordered instructions 5 and 7? The answer is we don't know because it is dynamic. And so, of course, it is almost impossible to find a best static schedule. So yes, there is opportunity for out of order on the GPU. And prior works have looked into it. So Luke, which was the prior state-of-the-art work, simply copied CPU out-of-order strategies over to the GPU. But the GPU architecture is different, and so are GPU workloads. And so it becomes increasingly important for us to reevaluate. 1, where do we want to place the out-of-order engine on the GPU? And 2, which out-of-order optimizations do we actually want to do? The main contribution of our work is that it shows that you can do out-of-order execution very efficiently on the GPU while giving significant performance gains. And now Ghost is actually a very detailed microarchitectural work, and while I would love to go over all the details with you in this talk, unfortunately we don't have the time for this. So I'm going to briefly describe our key insights and where do we actually implement Ghost. So the key insight of Ghost is that if you use the instruction buffer as the place of doing GPU out-of-order execution, you can basically remove register renaming, reorderings of loads and stores and stores and stores, and speculation, while getting significant performance improvements. And yes, you can ask me, all right, Ishita, you took away everything, and you gave us this very lightweight structure. What does it give you? So the thing is, ghosts don't occupy space, but you sure as heck will feel their presence. And how we do this is because we deeply studied the GPU microarchitecture and GPU applications and applied this knowledge together. So let's see where do we actually implement Ghost. So this is a very simple GPU pipeline. It has 5 stages. The GPU is an in-order processor. So instructions are fetched instructions are decoded instructions will be issued, operands will be collected, they will finally execute, and eventually write back. We've all seen this multiple times. For the sake of this presentation, I want you to focus on the decode and the issue stage, because this is where we do out-of-order execution. So in this stage, when instructions are decoded instructions are placed in the instruction buffer, which has space for every warp. Now, in every cycle, what the warp scheduler does is that it tries to find instructions which can be issued from across these warps and tries to issue them out. And it hides latency by very fast context switching among these warps. However, the constraint here is that the issue is strictly in order. So even if you utilize NVIDIA's multi-process service with multiple schedules running, if all of the oldest instructions will stall, you basically have a bubble in your CPU, and you have a stall cycle. What Ghost does is that it actually reimagines the instruction buffer as a pool of instructions. And now, even if all your oldest instructions were stalled, Ghost will actually go inside this instruction buffer and try to find an instruction which is ready for issue, whose all dependencies are satisfied without using any renaming, reorderings of loads and stores, or speculation. And to do this, Ghost actually makes some very few modifications to the pipeline. So we add the dependence checker, the Ghost scheduler, and the issue buffer. What to notice here is that all the modifications made by Ghost are constrained entirely within the decode stage. And the interfaces to all other parts of the pipeline are virtually unmodified. And if you go ahead and actually implement Ghost, it only increases the area of your GPU by a mere 0.007%, which is really small. And the power increase is a mere 0.1% of the GPU. And what to see here is that the change we are making is on this very small orange part of the SM, which already is area constrained. And so we went ahead and evaluated Ghost. And if you implement Ghost, what you will find is that Ghost gives a speed up of 7% across application types. Ghost does not show any slowdowns for any applications. And finally, if you implemented Ghost in your data center GPUs, in an year, you would save the energy equivalent of the entire country of Zimbabwe, right? And we also compared Ghost against Luke, which was the prior state-of-the-art out-of-order work. Now what Luke did was that it reimagined the collector units as reservation stations. And what happens when you do that is that all your backend stores now actually become collector unit structural hazards. And what happens is that we show that unlike Ghost, which is at least as performant as baseline, Luke will show significant drops in performance. Ghost has a maximum higher speed up than Luke, and also Ghost shows a much better performance than Luke. Now there was another work which was SoC GPGPU, which came out very recently. They made a similar observation as Ghost at the same time. However, what they do is that they don't remove instructions from their instruction buffer as the program executes until the instruction writes back. So they introduce a different kind of stall, which Ghost does not have, and they also show some slowdowns in applications. So the takeaway from my talk is that, yes, out-of-order execution on the GPU is very important. Ghost shows a way in which you can do this very effectively, and it shows very good speedups. And if you went ahead and implemented Ghost, you would save the energy equivalent of Zimbabwe. So please read our paper to know more. There's a lot of details in there that I had to gloss over. Thank you so much for attending my talk.
Sorry. All right, we have time for a couple questions. So if you just step up to the microphone, state your name and affiliation. I'll start off with one, in that Ghost is trying to apply some kind of CPU principles to enhance performance of the GPUs. What are your thoughts on going the other way? Should we try to take more GPU approaches and try to augment the CPUs?
Thanks for the question, Gabe. So that is actually the next work I'm working on, which is so we learned a lot from Ghost that you can utilize things you learn from one microarchitecture and apply them to the other. So now we're trying to use CPU-like threads, GPU-like threads on the CPU and see if we can get more parallelism on the CPU that way.
Hi, great talk. Dimitrios Karlatos from Carnegie Mellon University. So in the beginning, you motivated this work with MPS, like a multi-process service, right? So how would this approach compare to streams, where you have thread-level parallelism?
So Ghost is not orthogonal to MPS. You can actually use Ghost with MPS and get even better performance. So we already exploit the TLP GPUs have and add ILP to it.
And how would it compare to streams?
The performance?
No, in general, as a concept, can you leverage streams on top of Ghost?
I don't think I understand the question.
Can you leverage streams on top of Ghost? So have both streams and Ghost?
Yeah, I mean, you can definitely leverage streams on top of Ghost because streams will be running on different warps. And what we do is reordering inside a warp. So even if you have different streams, Ghost can work very well with them.
OK, thank you.
Thank you.
All right, let's thank the speaker again. We'll get the next speakers up. All right, while we get set up here, our next speaker is Liu Yunzhe, is a fourth-year PhD student at ICT-CAS, and he's been a lot of research interest in computer architecture and CPU microarchitecture. He's also been doing a lot of work as an intern with Wang, with many of you all know that company. And so, well, go ahead and take it away.
Everyone, I'm Liu Yunzhe from Institute of Computing Technology, Chinese Academy of Science, and I will introduce AVM-BTB, Adaptive and Virtualized Multi-Level Branch Target Buffer today. And firstly, I will introduce the relevant background. Fetch Directive Instruction Prefetching, FDIP, is commonly used in modern processors, and it uses a branch prediction unit, BPU, to generate fetch requests and uses requests to fetch and prefetch instructions. FDIP performs exceptionally well, but it heavily relies on the accuracy of the BPU. BTB is an important component of the BPU, which stores mappings from branch addresses to their respective target addresses. And all previously encountered taken branches in the instruction stream will be stored in the BTB, and it is responsible for identifying branches in the instruction stream and providing predictions of branch targets. BTB is highly sensitive to both capacity and latency, but large BTB is difficult to achieve low latency, so modern processors tend to use multi-level BTB. And the subject of this study is just lower level BTBs like L2 BTB, which are larger but slower. To further enhance the performance of such a system, there are 3 challenges, and the first challenge arises from the increased demand for SRAM due to the growth in BTB capacity, but SRAM resources are limited. And secondly, there have been emerging studies on BTB recently which have set higher thresholds for subsequent research. Solely optimization BTB itself has become increasingly challenging to get performance gains. Thus, we aim to conduct collaborative optimization of multiple components of the processors. The third challenge just arises from the co-optimization, because co-optimization of multiple components often results in high implementation difficulties, such as significant wiring delays or layout challenges. And in this study, we used a completely refactored version of ChamSim, and it's calibrated to conform to real processors with many new features. The traces include IPC1, CVP1, and various real-world applications with significant front-end pressure. And these 1,200 traces exhibit distinct characteristics and ensure the good applicability of our research. The strategy of this paper is to borrow SRAM from iCache and UOP cache for BTB when a larger BTB capacity is needed. And this strategy is based on 4 observations. And the first one is that BTB requirements vary significantly among different applications and even among different running stages of the same application. And we can see that many traces require fewer than 2,000 BTB entries, while there are also a considerable number of applications that need over 20,000 BTB entries. And we can further divide each trace into 100 segments and collect the BTB demand within each segment, and then compute the variance of these data within a trace. And we can see that some applications exhibit significant variance, indicating large differences in BTB demands across different running stages. Hence, simply increasing BTB size may not always bring benefits. In fact, after increasing the L2 BTB from 4K entries to 8K entries, nearly half of the traces did not benefit from it, causing the wasted opportunities costs. Therefore, static BTB design makes it difficult to meet the variable requirements of applications. The ability to dynamically adjust the BTB capacity is preferable. And the second observation is that in front-end overloaded scenarios, the performance of BTB is more critical than that of iCache. Moreover, improving the hit rate of BTB by increasing its capacity incurs less overhead compared to enlarging iCache. iCache is very important, but when the instruction footprint is large, storing all hot instructions in iCache requires unrealistic amounts of SRAM. To cover 90% of commonly used instructions, iCache needs to be over 1.5 megabytes. In contrast, a BTB with around 96 kilobyte SRAM can cover 90% of commonly taken branches, as it only needs to store once taken branches. And we'll find that only around 18% of the instructions are branches, and only half of them are once taken. Improving the BTB hit rate not only reduces the expensive branch prediction errors, but also helps FDIP more effectively prefetch instructions to compensate for the insufficient capacity of iCache. We found that in front-end bounded scenarios, the performance gains brought by the ideal BTB is far more than that of ideal iCache. Therefore, in front-end bounded scenarios, we may dynamically lend the SRAM of iCache to BTB to achieve an overall performance improvement. And the third observation, UOP cache performs poorly in front-end bounded scenarios. Sometimes its hit rate is even below 50% and fails to bring power consumption reduction and performance gains, as we expect. So it might be beneficial to repurpose its SRAM for BTP to enhance overall performance. The above three observations illustrate the importance of dynamically balancing SRAM resources and identifies the potential sources from which we can borrow SRAM for BTP. The fourth observation addresses when to borrow and return these SRAM. Firstly, we can borrow SRAM for BTP when the BTP error rate is high. This is trivial, but it's non-trivial to determine when to return these SRAM. And we found that in multi-level BTP, for example, if the L0 BTP can meet the needs, most BTP requests will be filtered by it, and leading to a sharp decrease in effective accesses to the L1 BTP. Therefore, we can judge whether the BTP demand has been satisfied at a certain level of the multi-level BTP by examining the difference in effective accesses between different BTP levels. Hence, we can dynamically adjust the BTP capacity based on these BTP metrics, which can be acquired by hardware counters. Combining all four observations together, we have the AVM-BTB, which dynamically borrows SRAM from iCache and UOP cache based on hardware counter information and use these SRAM as BTB. To avoid drawbacks like long wiring delays, we select adjacent components in the front end. We utilize all UOP cache data RAM and half of the weights of iCache data RAM that are closer to the BTP for co-optimization. And these RAMs support mode switching, transitioning from cache mode to BTP mode when necessary. And this BTP in cache, along with the original multi-level BTP, further form a multi-level BTP structure, including the original L0, L1, L2 BTP, and BTP in UOP cache, and BTP in iCache. And the switching algorithm is as follows. We collect hardware counter information every 1 million dynamic instructions, and when the BTP error rate exceeds 1%, activate BTP in UOP cache. If the BTP error rate still exceeds 1%, proceed to activate BTP in iCache. And under the premise of a BTP error rate below 1%, if the effective access of BTP in UOP cache exceeds 6 times the effective accesses of BTP in iCache, we deactivate BTP in iCache. Similarly, if the effective accesses of L2 BTP exceeds 6 times that of BTP in UOP cache, we deactivate BTP in UOP cache. And here's the evaluation. And in terms of area, SRAM occupies the vast majority of the BTP area, and our method, AVM-BTB, does not introduce additional dedicated SRAM for BTP, so the error increase is minor. However, if we directly expand the L2 BTP capacity, it would increase the error dramatically. And in terms of timing, the additional virtual BTB introduced a wiring delay of 180 picoseconds and an additional 3 layers of logic gates. And in our design, AVM-BTB serves as a 3-cycle readout lower level BTB, so it does not hurt the timing. We compared our method with the setups that directly increase L2 BTB capacity, and AVM-BTB improves the performance by 18% and 3% compared to the 8K and 4K entry setups, and achieved 99% of the performance of a 12K entry L2 BTB. And we also examined the power consumption of the front-end components, and our methods achieved a power reduction of 319 and 31% compared to the setups enlarging the L2 BTB. When compared with other state-of-the-art BTP optimizations, we select the BTP compression work, BTP-X and PDAT, the BTP prefetch work, confluence and shotgun, and the co-optimization work between BTP and last level cache, phantom BTP. And in comparisons with these 5 works, AVM-BTB maintains a leading position on most test suits and exhibits the highest average performance gains. And additionally, AVM-BTB is not conflicting with all the aforementioned works and can be used in conjunction with them. And we evaluate the combination of BTP-X and phantom BTB with our AVM-BTB and gets better performance improvement. And we also do a lot of sensitivity analysis to set the default values for those parameters like the BTB error rate threshold, and we also leave some control status registers for potential runtime modification of these parameters. And that's all, thank you.
All right, once again, please step up the microphone with any of your questions and state your name and affiliation.
Oh, thank you. I want to ask, what about the design without UOP cache, as many processors do not have such structure?
You're right, and we all know that x86 tend to use UOP cache, and processors like ARM, they use UOP cache from Cortex A77 to A710, and Samsung Exynos also use UOP cache. But we do consider processors without this component, and the performance gains reduces from around 18% to 13%, and the extra capacity will bring marginal benefits. So in case of processor without UOP cache, our method still can have a lot of performance gains.
Thank you.
Thank you.
Hi, Gilles Pocam, Intel Labs. Good talk. So I have two questions. First question on your slide, you had some bold claims that increasing the size of the BTB or replacement policy of the BTB are limited. Do you have data to support that? Second question, what infrastructure are you using to modelize? Is it ChemSim?
Can you repeat your question?
So the first question is about the claim that you're having on your first or second slide about limited value of increasing the size of the BTB or adapting a replacement policy or prefetching or whatever. So I think you have some claim like that in the second slide. And the second question is, what infrastructure are you using to model the micro-op cache change and such? Is it ChemSim?
Sorry, I didn't catch your first question. And the second question is that what modification we do to the ChemSim, right?
Sorry, say it again?
Sorry, can you repeat your second question?
ChemSim, you're using ChemSim for this?
Yes, we use ChemSim.
All right, thanks.
And the original ChemSim does not simulate UOP, right?
So how do you do then? Because you're using ChemSim and then you have some very bold claim about micro-op cache. It's very interesting.
Yes, we do the modification, and any instructions except vector instructions can only modify one memory location and one targeted physical registers, and any instructions modifying two registers will be split into two UOPs and occupying two slots in UOP cache and other pipeline slots after the decoding stage.
I can take this offline. Thank you.
Let's thank the speaker again. Okay, for our last talk of the session, a great pleasure. It's a rare treat for ISCA. We're actually going to have two speakers for this last paper, and they're actually both undergraduate students as well, so very, very impressive. We're going to have Aamodt, Bhatla, and Navneet, who are both undergrads at IIT Bombay, so they've made the long trip over here. They're part of the Casper research group led by Professor Panda. Navneet's actually going to be joining Georgia Tech for his PhD in the fall, and Aamodt is going to be pursuing his master's from IIT Bombay. So please give a really warm welcome to our rising undergrads.
the Maya cache, which is a storage efficient and secure, fully associative last level cache. So just to give a brief background what caches are. So most of the modern computer uses a smaller and faster memory as compared to a DRAM, so as to fetch the data quickly and in turn improve the performance of the overall system. Now this is a very generic cache hierarchy that is being used in most of the modern systems, where there is a private L1 and L2 cache for each core, and then there's a last level cache which is shared among the cores. Now these last level cache is prone to something called as conflict-based side channel attacks, which is a security issue since 2015, where from an attack called prime plus probe, where an adversary can populate the cache lines and it can monitor the victim accesses. So if the victim accesses a particular cache line and then evicts the adversary block, it can probe into the cache and figure out what kind of addresses the victim is accessing. And if those addresses are secret dependent, then the adversary can get to know that, which pose some security issues. So this is because when an adversary probe the cache, it accesses the cache and finds cache misses for its block, and hence it figures out what victim is accessing. So how to defend these? So in past 3 years, there are various proposals like to randomize the set mapping. This is basically done to block the attacker's view of the set, and hence, so there's no direct correlation between an insertion and an eviction, because there is a randomizing function which is secured with a key which the attacker doesn't know. Now, but the attackers are smart and they find an indirect way to figure out what is the set mapping through something called an eviction set discovery, which kind of gives a set of addresses that maps to the same set. So this breaks the randomized idea that Caesar proposes in Micro 2018. Now then there's another idea that is an improvement of Caesar, which is Caesar S, which kind of separates the cache into 2 skews so as to further obstruct the attacker's view of the set mapping. But it was also broken quickly in 2021. So now the reason that the eviction set discovery is possible is because of something called a set-associated eviction. So whenever an entry is put into the cache, the evicted candidates belong to the same set. So then there's something called set-associated eviction that occurs, and through that the attacker is able to figure out what kind of addresses maps to the same set. So what is the fix? Now, an ideal scenario would be to use a fully associative randomized cache where there's no correlation between the incoming line and the eviction candidate. So the attackers get no idea what is being accessed by the victim. So a no set association makes it harder for conflict-based attacks. But there's an issue with using a fully associative randomized cache, which is, it is expensive in terms of power and energy. So if you consider the lookup has to be the entire cache to figure out which entry we are trying to find. And if you look at a set associative cache, the lookup is pretty small because you just have to look at the particular set, and so the power and latency is small. But set associative caches gives you something called set associative evictions, and that poses security issues. So how to get the best of both worlds? Can we get security of a fully associative cache with set associative lookups in order to minimize our power and latency? So the answer is yes. In 2020, there was a proposal named Mirage in Usenet security, which suggests that you decouple the cache into something called tag store and data store, and give extra entries in the tag store. So what's happening here is you have a tag store, which is, there's no set mapping as such in tag store, so it's like a fully associative cache. And then you have a set associative tag store where the lookups are set-based. And there's also a randomized mapping for those sets. Now, and these entries in tag store and data store are connected with pointers, so you don't lose track of them. And whenever there is an eviction in the data store, it maps to a corresponding tag store and evict that. Now, since the eviction is globally random, there is no guarantee that an eviction is from the same set in which the insertion is happening. So in this way, this mitigates something called a set-associated eviction, but not completely. What Mirage suggests is you should have the number of invalid entries, the white boxes you can see, that is the extra invalid entries in the tag store should be above a particular threshold in order to completely mitigate set-associated eviction, which is in this case 6 extra ways. So using these invalid tag ways and a decoupled nature of the cache, we can achieve security which completely mitigates set-associated eviction. But there's some issue with this Mirage design is that because of the use of forward and reverse pointer that is used to connect the tag entries and data entries, along with the extra invalid tag ways that Mirage uses, it imposes storage and power overheads, where the storage overhead is above 20% and power overhead is around 19%. Now, can we fix this? So our analysis on a non-secure 16-way 16 MB baseline and the 16 MB Mirage suggests that there are more than 80% dead block in the last level cache. That means the data store is not being efficiently used in these cases. So the idea is can we reduce the data store size, but a naive reduction of the data store size will degrade the performance. So we need to do some microarchitectural improvements to achieve our goal.
Right, so we bring in the idea of reuse, which was first introduced in 2013. According to it, on a first access to a cache line, we only bring in the tag into the tag store, and only on the second access do we bring in the data. This helps ensure that the data is stored only when reuse is detected. So if we look at Mirage again, so Mirage had some extra invalid tag ways to ensure security. With our Maya cache design, we have a smaller data store, and we bring in the concept of reuse. So again, we have some extra invalid tag ways to help ensure security. But because of the fact that data entries are much more expensive compared to a tag entry, we are able to ensure 2% storage savings compared to a non-secure baseline, whereas Mirage had a hefty 20% storage over it. This is an overview of the Maya cache design. So here you can see that we have two ciphers which decide the set mapping to each of the SKUs. We introduce a priority bit in the tag store, which helps us track reuse. So we can have two types of entries now in the cache. So a priority 0 entry has only tag and no data, and a priority 1 entry has both tag and data. We perform random global data eviction from the data store with the help of reverse pointers. The Maya cache design has more tag store entries, but fewer data store entries. And since the fact that data store entries are more expensive, we end up with storage savings. So for the security model, we use a bucket and ball model. Here, buckets represent cache sets, and ball represents cache lines. There is a capacity to how many balls a bucket can hold. And in case a bucket exceeds this capacity, we get a ball spill, or an SAE. So here we show that the probability of getting a ball spill or an SAE is extremely low with Maya. Maya can ensure no set-associative evictions in more than 10^16 years. This brings up the question that if reuse can be exploited to mount an attack. So Maya makes use of domain IDs for each tag store entry. This helps ensure that the reuse pattern is isolated between the attacker and the victim, and helps prevent any reuse-dependent fill-based attacks. Coming to shared memory attacks, again, the use of domain IDs helps ensure that 2 copies of the same incoming line address are stored in the LLC, and helps mitigate any shared memory attacks as well. This is the simulation framework that we use. We use the Shamsim multi-core simulator with an 8-core CPU, private enval into caches, and the baseline is a shared LLC with 24-cycle latency and 16 MB data store, whereas Maya has a 28-cycle latency and a 12 MB data store. This graph summarizes the performance results for Maya and Mirage. So these results are for some Spec 2017 and gap traces, normalized to a non-secure baseline. Here we can observe that Maya has a marginal performance improvement over a non-secure baseline. This table summarizes the evaluation results for Maya. We can see that Maya has a marginal performance improvement of around 2% over a non-secure baseline, as well as savings in terms of storage, area, energy, power, all while maintaining complete security against conflict-based attacks. To summarize, Maya is a randomized, fully associative last-level cache that uses additional tag entries and fewer data store entries. It uses a reuse-based insertion policy and ensures complete security against conflict-based attacks by ensuring no set-associative evictions in 10 power 16 years. Maya provides a sweet spot in terms of security, performance, area, and energy requirements. You can refer to our artifact by scanning this QR code. Thank you.
All right, we're already queued up, so please state your name and affiliation before asking your question.
Hi, Daniel Jimenez, Texas A&M University. Great talk. Thank you for using ChampSim. What's your baseline replacement policy? Is it assuming it's like LRU, and then you go in and do something to exploit the deadblocks? Would it be good to have a baseline replacement policy that takes into account the work on deadblock prediction, or the work that modern processors, they don't use simple replacement policies. They use replacement policies that exploit the fact that many blocks aren't reused, and they also have complex prefetchers.
So we make use of the Hawkeye replacement policy for the baseline, and we also have prefetchers turned off. So we use the IPCP prefetcher. So we felt that that was a strong enough baseline to compare against.
Wait, I'm sorry, what did you say the baseline replacement policy is?
Hawkeye.
Okay.
Yeah.
Good. Thanks.
Amir Jalil, NVIDIA. Nice work and nice talk. Your work effectively is reducing the data store from 16 megabytes to 12 megabytes. And I think you've exploited workloads today that are not efficiently utilizing the last level cache. But suppose you have a workload that actually did fully utilize the baseline 16 megabyte cache, a workload that's tiled to it, right? So in those cases, you are unnecessarily going to be penalizing a workload that was using that. So have you looked at this, and how would you go about addressing workloads that are tiled to a given cache size?
So yeah, you're right about that. So there are some workloads. So for example, we can observe that with gap workloads, they do require a larger data store. And we did get a performance hit in those cases here. So in those cases, the reuse insertion policy didn't really give us much of a benefit.
So you're trading off potentially performance for security at ISO area.
Yeah.
Shaigul On from Google. So my question is this: what happens if your else is distributed? How does that impact your assumptions?
Can you repeat your question?
What happens if your LLC is distributed, so only a certain set of addresses can go into any slice? That's typical with large SoC designs.
So are you talking about slicing or partitioning?
Partitioning.
There have been a lot of proposals based on partitioning which help with security, but they usually have a very high performance overhead.
Okay, thanks.
All right, thanks. Okay, so that concludes our session. A huge thanks to the speakers for all three papers for being timely on their presentations. We now have a coffee break in the main hallway, so please continue the discussion there. Thank you all.
Thank you.